Differential equations 5.1, picking back up at the end of our last problem. We're trying to solve for y here. So what we could do very quickly is just subtract a 1 from both sides. We'd have 2y over x is equal to, now you could make this c3 over x squared if you'd like, minus a 1. But getting y alone, you can see that we really want to get rid of this 2 over x, so we can multiply through by the reciprocal on both sides. Multiply through by x over 2. Here the x's cancel, the 2's cancel, and as we distribute over this way, we'll have a constant. You could call that c3, or you could just call it a c if you would like. One of the x's cancels down below, but you'll also have a 2 down below. And then right here, as we distribute x over 2 to the 1, we have minus x over 2. So that's going to be our final answer. As we continue on, as we take a look at one more problem, let's go to the last page over here. And we have an m and we have an n. And you can see that our m is actually way simpler looking than what we have for our n form. Our m, if we were to plug in and substitute in a tx and a ty, we would get ty, which is really t to the first times m. If I were to substitute a tx and a ty into our n function, well, that's a lot more involved. We'd have a tx, and then inside here we'd have the ln of tx minus the ln of ty minus a 1. And tell you what, whenever you have two logs that are being subtracted, we had a wonderful property that we could condense those logs. And in so doing, you can see that the x's are going, not the x's, but the t's are going to cancel out. You're going to have the ln of x over y. And then, tell you what, I'm going to re-expand that. I'm going to now reverse and write that as ln of x minus the ln of y minus 1. And the reason for doing that right now is you could see that this whole big expression here was n. So I have t to the first times n. And you can really notice that the degree for both of these is 1. Alpha would equal 1. So this is a homogeneous differential equation. That means that we can go ahead and use a substitution to help us out. You can see that the simpler differential is dx. So because dx is so much simpler, we're going to immediately make the substitution x is equal to v times y. Remember, we're either going to do y equals uv or x equals vy. And at this point, we can take a derivative dx using the product rule. Here on the right-hand side, we'd have a v dy plus y dv, or dv times y, it's the same thing. And now, everywhere in the original problem where I see an x, I'm going to make a change. I'll replace that with a vy. Everywhere where I see a dx, I'm going to replace that. So yeah, again, what we could do, we could even make it color-coded if you'd like. You know, everywhere where we see an x, we're going to make a change, right? Everywhere where we see a dx, we're going to make that substitution as well. So what's going to happen when we do that? Well, this original problem becomes, well, you've got a y, but your dx becomes v dy plus y dv plus, well, x is going to change. X is now going to be vy. We'll have the ln of vy as well, minus the ln of y minus 1, and then we'll have a dy. Now, what I like to do, and if you've got a different color, you can do that. I just like to see what happens as we distribute all of this. We'd have a Vy dy plus a y squared dv. Over here, we would have a quite a bit messier form, a Vy ln of Vy minus a Vy ln of y minus a Vy. And of course, that's all associated with your dy. I didn't even distribute the dy in there. I guess what I want us to immediately take notice of is that, we have a minus Vy dy right here, and we have a plus Vy dy over here. So just remember that ultimately our goal is to separate variables and to, move forward from there. So really, with this first big bracket, you could see that the Vy dy and the minus Vy dy would be gone, leaving us with a y squared dv right here. And then we'd have this whole big messy expression over here as well. So, as we're coming back here, you can have your Vy ln of Vy minus Vy ln of y, and that's your dy. So ultimately, we need to do some moving around. And tell you what, let's get one differential on the right side, the other on the left. I'm going to move this negative y squared dv over to the right. And then we've got on the left-hand side, tell you what, it's kind of ironic, I'm going to actually factor out a Vy from that. Of course, this is what we have with our dy. And the whole purpose is to get our dy's and so forth all together. Now, again, here's that little trick that we saw when we were showing that our functions were homogeneous. We could, again, say, now, wait a minute, two logs that are being subtracted, I can condense them and immediately see that those y's cancel out. So things are looking up, things are cleaning up a little bit. So we've got our Vy ln of v, and here's your dy. And over here we've got our minus y squared dv. So tell you what, everything with y's we want on the left side, everything with a v we want on the right. So I'm going to divide both sides to do some moving around. I'm going to divide both sides by negative y squared, because I want my y's on the left. I want to get rid of this thing right here. Simultaneously, I'm going to divide by v ln of v. And that way these v's cancel out, and this ln of v is going to be gone too. So cleaning this up, what do we have? Well, y over negative y squared, you're going to have a negative 1 over y. And this is a dy, of course. Right over here, you'd have a 1 over v ln of v and dv. And we're going to integrate right now. We're just going to keep going, integrating. The right side, I think, is the side where we're, going to be a little bit more cautious. You can think, my goodness, how do we deal with that? Use substitution, actually. Let's let u equal ln of v. And if we let u equal ln of v, that means du would be 1 over v dv. So really very nicely on this right-hand side, you can see that we've got our u down here, but the 1 over v is going to get canceled. The 1 over v dv is just going to be a du, right? So all that just becomes a du. And over here, I'm going to factor out that negative as we finish this up. Well, you can see very similar setups. This is going to be the ln of the absolute value of y. Over here, we'd have the ln of the absolute value of u, and of course we could do a plus c. Now the u, of course, is just the ln of v, And we're going to go ahead and say this is the ln of the absolute value of the ln of v. Look at that. That can look a little funny. And then over here, we've got the negative ln of y. Now, at this point, I do want to tell you that we could exponentiate both sides. That's definitely what we did previously. But tell you what we could also do. I want to show this to you. I'm going to add an ln of y to this right side. That can look so strange at first. You might wonder why we're doing that. I just want to get my natural logs together. I'm going to subtract a c from both sides, move that constant over here, and you can think it's negative c, but it's really, at the end of the day, just going to be a c itself. It's a constant. Some of you can see what we're doing already. When I've got the ln of a plus the ln of b, that can get condensed into the ln of a times b. So this is an alternate way to punch this out. That's going to be y multiplied to the ln of v. Look at that. Why might that be a little bit easier? Well, my goodness, hopefully you can see what we're talking about right now. This got cleaned up in a hurry. Now, our original substitution was x was equal to vy. So that means that v itself would be x over y. So I'd have the ln, so here's y times the ln of x over y. So look at that. We've got a nice setup. We can exponentiate right now. As we exponentiate, e to the right side, e to the left side. E to a constant is another constant. We could just call that C2. And then what are we left at over here? Well, the absolute value of y times the ln of x over y. And getting rid of the absolute value, of course, you could say, well, that's a plus minus. We'll have a plus minus constant. And you could just write that plus minus constant arbitrarily. This is really as far as you can go. Just wanted to show you this alternate way of getting two logs together and condensing them. That could be a very helpful way to solve.